extremely talented young researchers who work on extensions of several matching programs in interactive. And I thought that typically here, as I mentioned, the speakers are those who have fundamental contributions in the past. So I thought that it would be nice if someone from the next generation would give a talk on the research results. And it was not easy for me to pick one person among the many, but at least let me mention the name who has a very important contribution in this area. Tamás Király, Laci B, Zsolt Fekete, Jászin, and Mishi Jászin Szabó, and Mishi Barász, and I hope I apologize if I forgot this video. But anyway, the selection had to be made, and it is Gyula Pap, who, in my view, I'm sorry for the big words, excellent results. If, say, 2 years ago someone tells me that this is possible, I would say this is not. With the matching algorithm, Jack's matching algorithm, non-bipartite matching, it's a wonderful piece. There is one difficulty. There are several extensions and generalize the algorithm, which works so nicely for matching. This is not easy at all. If you look at Mader's theorem, it was mentioned several times, to get that it's an extension of matching thing, and if you want to find an algorithm, that's a difficult thing. There is another model, there are several other models. And now I think you see that made a breakthrough in this direction, and now listen. Thank you, Jack. Problems. A couple of them here. The relax-reduce approach is put together from two constructive lemmas used as black boxes in a possible algorithm. These constructive lemmas admit direct, easy proofs using local manipulations rather than a global augmentation structure. So let me show a very easy example to apply a relax-reduce proof or algorithm. Now, Koenig's theorem determines the maximum cardinality of a matching in a bipartite graph by the degree constraint at most 1. That is, we cover the edge set of the bipartite graph by stars. So, in order to give relax-reduce proof for this theorem, we need to give a relaxation problem, and here a problem which is very easy to solve. Given a bipartite graph, a set of edges is called A matching if the edges in this set hit pairwise distinct nodes of A. So this is a relaxation of matching. It's an easy observation, analogous to Koenig's theorem, that the maximum cardinality of an A matching can be determined by a cover. We only use stars like that. To see this,
an A matching is constructed by picking an arbitrary edge from each non-isolated node in A. This is easy. To prove Koenig's theorem, consider an arbitrary matching in the graph. Check whether n is a maximum A matching. This is easy. Well, if it is, then we are done. The observation implies equality in Koenig's min-max formula. Otherwise, there will be an exposed node in A, which is not an isolated node. That means that we will have a dashed edge like that or that. In the first case, we can augment. That is nice when thinking of an algorithm. In the other case, we have that funny constellation. The second part of the proof, we construct a reduction for this constellation. We just construct a reduced graph G prime by deleting the white dot and merging the two yellow dots. Matching in G prime is constructed as the image of M. Now, by induction, Koenig's theorem holds for G prime, hence there is either a larger matching or a cover verifying optimality of our matching. Now, both of these cases extend to the original graph G. So, augmentation, we just add the edge AB or BC to get a larger matching in G. And also it is easy to see that verifying cover, if we have a verifying cover in G prime for N prime, and X does not contain the yellow dot, so X plus B will determine verifying cover in the original graph. That is the proof. Now, the two previous slides can be summarized by the three-way lemma and this red lemma. Three-way lemma says that either our current solution is optimum in the relaxation, or we can augment, or we find some kind of a constellation. The red lemma constructs a reduction for this constellation. So these two lemmas can be put together to give an algorithm finding a maximum matching in a bipartite graph. We maintain the graph, bipartite graph, and the matching. You can see what I mean. The red arrows show you that there, if you find augmentation or a verifying cover in the reduced graph, you can extend it to the original one. Where are alternating paths? Now, after a sequence of reductions, if you have a yellow dot contracted a couple of these constellations, the pre-image of such a yellow dot will just be an alternating forest. So there are alternating paths, and we put in a black box lemma. Now, this is for Koenig's theorem. Let me show you another min-max formula which can be proved by relax reduce principle. Also, an algorithm follows. That will be square-free simple two matchings. First, let me tell you this. This is the relaxation used in the relax reduce scheme. So, simple two matching, that is a set of edges in given a bipartite graph. A simple two matching is just a set of edges obeying degree constraint at most 2. More generally, we assign node capacities 0, 1, or 2 to the nodes of the graph, and that gives degree constraints that we call a simple B matching. And we know that this theorem follows from bipartite matching theory, saying that the maximum cardinality of a simple B matching, simple bipartite graph, is determined by a cover using stars and single edges. Now, simple two matching that consists of disjoint union of paths and cycles. It is called square-free if the matching does not contain all the 4 edges of a 4-edge cycle. So at most 3 of them. Now, Hartwigsen was the first who claimed good characterization of the maximum cardinality of a square-free simple B matching. He showed half integral. He showed that it is attained by a half integral cover. Later, Zoltán Király proved that this optimum is also attained by an integral cover. Here we use stars, single edges, and capacity 3 squares in a cover. This theorem is interesting since the system of inequalities there, together with non-negativity, does not determine a totally dual integral system. So general theory does not apply directly. Also, no alternating path lemma is known for square-free simple B matchings. How to find a large square-free simple B matching by means of an augmentation structure? Such a structure is not known. A three-way lemma can be formulated as follows. Either our current square-free B matching is optimum in the relaxed problem, it is a maximum B matching, or we can augment, find a larger square-free B matching, or we find this constellation. So there is another same size square-free B matching and a square such that they fit each other like this I call a nice square with respect to n. So a square is called nice with respect to n if n contains exactly 3 edges of that square and at most 1 edge leaving that square. Then the relax reduce principle will be completed by showing the reduction of a nice square. But let me first show how to prove this three-way lemma. Suppose our square-free B-matching N is not a maximum B-matching, then there exists an augmenting alternating path P, that is an alternating path starting and ending with a node where the degree capacity is not exhausted. The symmetric difference is a larger B matching. If it is square-free, then we augment, we are done. Otherwise, now this is the key turning point of the proof, and so let me tell you how this works. So consider an alternating path as a process. We choose starting segment of this path, and we add an edge, delete an edge, add an edge, delete an edge. So we go 2 steps each time. Now, in the beginning there was no square. In the end, there was at least a square, possibly a couple of squares in the total symmetric difference. Now, pick the first moment when a square arises. Say mi is square-free, but in mi plus 1, so by mi, I mean the symmetric difference with the 2i long starting segment of the path. So if mi is square-free, but mi plus 1 is not square-free, I added an edge, deleted another one, hitting the same node, and exactly one square can arise. And convince yourself that this is exactly what we get. We get a nice square, nice with respect to mi. This is the proof of the three-way lemma. It is easy. The reduction of a nice square. I have not told you that the definition of a nice square includes that we require the node capacities of the 4 nodes of the square to be equal to 2, but so that is what we get. So capacity will be 2. Now, so given G capacity B and the square-free B matching N, nice with that square. The reduction is defined by constructing G prime, merging the 2 yellow dots of the square and merging the 2 pink dots of the square. And now, in G prime there will be no edge between the merged nodes. This is, by definition, I put no edge there. Also, this construction, by this construction, a square-free B matching with the B prime matching is constructed in G prime, where the capacities B prime are defined by B for the old nodes and 1 for the new nodes. And this reduction is equivalent in the following sense. Given, suppose we get somehow a larger B prime, a square-free B prime matching in G prime, then I claim that you can construct a square-free B-matching in G by adding appropriate 3 edges of that square. It will be square-free. It is quite easy to check. Also, if M prime would be a maximum, if we would have a verifying cover for M prime in the reduced instance, then I claim that you can probably add a couple of things to the cover, to the pre-image of that cover, so that the value of that cover only gets bigger by 3. So that is what we need for this equivalent reduction. A similar an algorithm of a similar architecture is put together from these 2 black box lemmas by maintaining a graph with capacities and a square-free 2 matching. We do the same thing. After a sequence of reductions, if we can augment, then this augmentation extends to the original graph, or if we find a verifying cover in a reduced after a sequence of reductions, then that extends by the red lemma to the original graph, and optimality is proved by that cover. And so, let me show you a couple of other problems for which relaxed reduce algorithm can be constructed. Maximum matching in a non-bipartite graph is found by Edmonds' matching algorithm, and in a specific way, the relaxed reduce approach gives Edmonds' matching algorithm. The difference is that as we only have these black boxes maintaining the graph and the matching, we do not maintain the alternating forest. But this means that we get worse running times. However, Edmonds' matching algorithm we can put together from these black box lemmas. The 3-way lemma for matching claims that either our current matching is a maximum fractional matching, or there is a larger matching, or we find an odd cycle which is alternating with respect to another same size matching. This is important. So here I'm looking for an alternating odd cycle adjacent to an exposed node. Since only the contraction of such an odd cycle will be an equivalent reduction. This concept extends to generalizations of matching, of non-bipartite matching. Here's the how many minutes? So the path matching problem is given as follows. We have an undirected graph G and 2 disjoint node sets, T1 and T2. Path matching is a 0, 1, 2 vector on the edge set, such that its support looks like this. I'm mean X is it consists of no disjoint paths from T1 to T2, or from T1 to here in the middle, or from here in the middle to T2, all with weights 1, and some disjoint edges in the middle with weight 2. So this is a path matching. It is not so easy to construct a combinatorial algorithm to find a maximum size path matching. The size is just the sum of the entries of the vector. However, this three-way lemma can be formulated, where the relaxation is the path cycle matching problem, slightly artificial problem, for the purposes of this three-way lemma. Here, in a path cycle matching, I also allow port cycles with all one entries in the middle. So this is how a path cycle matching looks like. And the three-way lemma says that either our current path matching is a maximum path cycle matching, or there is a larger path matching, or there is an port cycle which is nice with same value path matching. So this is here. It is also important that in case C, I start with x, but I find another x prime of the same value, which is nice with an odd cycle. Nice, that is, it is at the ending segment of such a so-called half T1 path, or it is an alternating path with respect to those two weight edges in the middle, like this. And the reduction lemma also extends for the contraction of a nice odd cycle. These two lemmas together combine to a maximum path cycle matching algorithm. Maximum path matching algorithm. Here the path cycle matching problem is a nice relaxation, since it reduces to bipartite matching. This is how I check case A. I won't tell you the proof. This three-way lemma has a direct, easy proof. Now, some sort of a three-way lemma also holds for Mulder's problem of packing no disjoint A paths. Here I used the fully no disjoint version. We are given a subpartition of the node set. We are looking for the maximum number of fully no disjoint A paths, that when path is an A path if it starts and ends in two distinct members of this subpartition. The three-way lemma for A path says that either our current packing, an integer packing, that it is a maximum fractional packing of A path, or there is a larger packing, or we find a nice constellation which looks like this or that. So we find this nice one of these nice constellations with respect to a same cardinality packing. Thank you for your attention.
like very much your reductions. I especially like your reductions. And I wonder if you can replace your three-way lemma by growing an alternating forest and making your reductions and continuing with the forest. Say for the square feet. Let's concentrate on the square feet.
I don't think so. I can maintain this augmented structure after contracting.
After making that reduction, well, you grow some kind of alternating forest to reach that point, right? But you feel that after you've made the reduction, you need the three-way lemma rather than simply maintaining the same device you had for finding the alternating forest. You don't think that works?
I think the reduction destroys possible previous alternating paths. It destroys them, and I don't see a way how to avoid that.
Thank you. Second question. Your covering paradigm suggests, immediately suggests linear inequalities that might apply as well for weighted objective functions. Do you know that the polytope you get analogous to these capacitated coverings do not give you the polytope of square free two matches? Do you know that the obvious candidate polytope is not valid for square free two matchings, or might it be?